Hello, I'm David Bolton of GoParallel, and today I'm going to be showing you the benefits of using OpenMP to speed up Fortran programs. OpenMP is an API that supports multiprocessing for C, C++, and Fortran on Unix, Linux, macOS, and Windows platforms. My setup is a Windows 8.1 i7 quad-core CPU with effectively 8 cores. The application I'm going to be showing you is one on matrix multiplication by John Burkhart, an instructor at Florida State University. For this demonstration, I've set it up with OpenMP disabled, so let's run it and see how long it takes. I've chosen a size value of 650 for the dimensions of the matrix, i.e. each one is 650 by 650. This version of the program took 18.62 seconds to run. That's running without OpenMP. I'll now go to the settings and enable OpenMP. If you look closely at the code, you can see that we have the markup for OpenMP, lines like this and this where it's enabled, but the previous version ran without those being enabled because of this setting. I'll show you the setting now. And it's OpenMP properties, Fortran language, and you'll see process OpenMP directives, which is currently disabled. I now enable it to generate parallel code. And now I'll recompile the program. And let's run it and see how long it takes this time. And that is significantly better at 5.795, approximately a third of the time that it took the first one to run. Now let's have a look at the code and see exactly what kind of calculations are being done. This first double loop here calculates the angle equal to 2 times pi times I minus 1 times j minus 1 and divides by n, or actually a cast of n to a real because n's int. Then the element a of j is equal to s times the sine of angle plus the cosine of the angle. And s is defined as 1 over the square root of n up here. Note the OMP parallel share directive. This specifies which of the variables used between this part and this part are shared and which are private. The shared bit means that there's only one instance of them, so the arrays A, B, and C and the two constants n and s, they're only ever accessed once, while the private variables are those I, j, and k and angle, and those are different in each thread. The OMP do directive applies to the loops contained within. You can see that here. If the computations inside the loop are independent of one another, and the loop size is specified in advance, which it is with these do loops, then it can be parallelized. In fact, you can nest OMP do directives should you wish, but there's an overhead doing that. For example, you might want to do it here. The OMP FAQ on the omp.org website suggests that you should consider using an OMP parallel outside the outside loop, and then do an OMP do before the inner loop. All three sets of loops use OMP do, as you can see. Here's a tip for you: if you're working in Fortran and C or C++, OMP directives need a matching closing directive. That's these here in Fortran, but in C and C++ they don't. The second of the three loops here just copies the array A elements one by one to the B, and the third one is the actual matrix multiplication. If you look closely at here, you can see there's a third loop inside the other two, and that's used to sum up along the rows and the columns to do the matrix multiplication calculation. Thank you for watching this video. I'm David Bolton of GoParallel.